In the previous video, we talked about different approaches for solving the linear regression problem using TensorFlow. We talked about using the normal equation, which is a linear algebra technique that involves matrix transposes and matrix inverses, those kind of linear algebra calculations, and TensorFlow was able to TensorFlow can do that. But our emphasis was on the batch gradient descent, or BGD method, which is actually more general and is applicable to problems that are much more complex than linear regression. And we talked about the different ways for computing and using the gradients in TensorFlow. So for linear regression problems, we can compute the gradients manually by using linear algebra. Right? For problems that are more complex, TensorFlow provides the capability to evaluate the exact gradients automatically through backpropagation. So the gradient calculation can be applied to neural networks with arbitrary complexity. It doesn't have to be a linear regression problem. But for the linear algebra solution of the gradients, it's only applicable to the linear regression problem, right? But the TensorFlow's gradient automatic auto-diff capability is a lot more general than that. And the TensorFlow also provides some out-of-the-box optimizers that encapsulate the process of gradient calculation and descending along the negative gradients processes. Those things can be encapsulated by the out-of-the-box optimizers provided by TensorFlow. And we looked at the two examples of those optimizers. One is the gradient descent optimizer, the other one is the so-called moment descent optimizer, that kind of thing. But in our last video, we used a training dataset with only 5 training examples. And in practice, the total number of training examples can be much larger, right? And a more efficient way for training a neural network is actually the mini-batch gradient descent. So in this video, let's try to implement the mini-batch gradient descent for our toy linear regression problem. So for our toy linear regression problem, we don't really have a very large training dataset. So let's try to create a fake dataset. Just pretend we have some kind of dataset, and this kind of dataset is created by sort of using just the numpy linear algebra operations. You don't really have to understand how this those numpy calculations will carry out, because we haven't talked about numpy yet. In practice, if you are actually trying to apply exactly the same template to real data, you will not have this kind of problem, because for real data, you can just load the data into Python and then try to use the real data instead of trying to create a fake data, right? So we'll try to create a fake data set with 10,000 training examples. It's still very small, right? But that's it's probably enough for our purposes, for demonstration purposes, and we will use numpy for that purpose. So let's first import numpy. We will create 10,000 examples. So our input data matrix capital X and the ground truth vector Y will have 10,000 rows. Let's just n row equals to 10,000. In principle, for every training example, we only have like 2 input data, x1 and x2, right? If you don't exactly remember how our neural network is constructed, it's we have a diagram in the previous video, and you can sort of take a look at that. We only have like 2 input data, x1 and x2, and the input data x0 is actually accounts for the bias term. It's fixed. X0 actually has a value that's fixed at a constant 1. So in principle, we can actually set the number of columns to just 2, right? And we'll account for the bias term later on by adding 1 to n co, basically. So now let's just say the number of columns is 2, and which will make our sort of numpy operation easier, right? And now we can actually use numpy to create a matrix of 10,000 rows and 2 columns. and filled with random numbers for the inputs x1 and x2. So let's say input data equals to np dot random, and then this function is going to take a Python tuple, and the tuple we're giving it is nrow ncol. So this particular numpy function is going to create a matrix with 10,000 rows and 2 columns, and this matrix is filled up with all random numbers. And then the input x0 that is fixed at 1 can then be concatenated into this random number matrix. So we can say input data with bias equals to np dot. So this syntax, if you are not familiar with numpy, this actually means concatenation, column-wise concatenation. It's C underscore followed by the square, a pair of square brackets means column concatenation. So the first column is going to be all ones. So this np dot ones function is going to create a matrix with all the elements filled up with 1, right? And the dimension of the matrix is going to be specified using a tuple. It's going to be n row and then 1, right? It's going to be 10,000 rows and 1 column, and then that's going to be the first column, right? And then we concatenate that with input data, that random matrix that we just generated. Right? So input data with bias is going to give you a matrix that the first column is all filled up with 1, and then the next 2 columns are all random numbers, right? So the first column is actually x0, and then the next 2 columns are actually x1 and x2, and the total number of rows is 10,000 because we have 10,000 examples. And then so this input data with bias, this thing is our fake input data matrix, capital X, right? So what will be our fake ground truth vector Y, right? So we have 3 weights, W0, W1, and W2. We have 3 weights. Let's assume that the true values of the 3 weights are 2.5, 1.7, and minus 0.8. And we create a numpy array for the true weights. Let's just call it weights true. That's 2.5, 1.7, and minus 0.8. Right. And the fake ground truth vector Y can be computed by doing a matrix vector multiplication using the input data matrix with bias, this thing, together with the true weights. Right? If you know linear algebra, so let's type ground truth equals to input data with bias dot. We're gonna call the dot method on this particular matrix, and then weights true. Input data with bias. Okay, so if you know something about linear algebra but don't know anything about the numpy, then there might be some kind of a misunderstanding here. This dot, right? In linear algebra, dot usually means inner product, right? But in numpy, this dot method defined on a numpy array actually means matrix multiplication. So input data with bias dot method, and then with the weights true as the input, it's gonna do a matrix vector multiplication actually. So this is the matrix, right? How many rows? 10,000 rows, 3 columns, right? And then dot weights true, it's gonna do a matrix vector multiplication with the weights true. Weights true is what? Weights true is gonna be treated as just to be safe, let me convert it into a numpy array. Otherwise, it's going to be treated as a Python list. and then maybe it's gonna have problems to match the dimensions. So input data with bias is 10,000 rows, 3 columns, right? And then when it's true, it's gonna be treated as 3 rows, 1 column. If I remember the convention in numpy correctly. Right. Let's just run this piece of code and make sure that we didn't actually make any mistakes. Okay, so it looks like it's correct. So weights true is treated like 3 rows with an undefined column, and then ground truth is treated like a 10,000 rows unspecified column. Okay, so that's fine. That's fine, right? So this dot is gonna do a matrix vector multiplication. It's not really exactly an inner product between 2 vectors, that kind of thing, right? That's one of the peculiarities of numpy actually. So from now on, we will pretend that we don't know the true weights. This true weights is hidden from us. It's given by God. It's not known to us, right? The only thing that we are given is this kind of fake input data with bias. That's a fake X, right? And it's also the fake ground truth, right? So that's the only thing that we know. These two fake input data and the fake ground truth of the 10,000 training examples in our fake training dataset, right? The weights true is hidden from us. We don't really know what weights true actually is, and we will try to actually recover approximations of those true weights, or sort of very close approximations of those true weights through mini batch gradient descent. Okay, so this part is like done already, right? So we have the ground truth data and also the input data with bias. So now let's try to build the computational graph. Let's do graph construction. Let's construct the graph. In fact, the code is actually very similar to the gradient descent code that we were writing in the previous video. In fact, the only difference is that the tensor capital X and the small y constant tensors that were constant tensors in the previous video now must be replaced with the placeholders, with the TensorFlow placeholders. So before constructing the graph, we need to import the TensorFlow module, right? And then before we adding any nodes, let's clean up. Let's reset before the graph. Let's just clean up all the existing nodes in here. Now we define 2 placeholders, X and Y, and the values inside those placeholders will actually change from mini batch to mini batch, right? So that's how mini batch actually works. So every time you actually, for every iteration, the X and Y values must be replaced with the value in the next batch, basically. So X is gonna equal to, in the previous video, X was defined as a TensorFlow constant, right? But now it's a TensorFlow placeholder. We talked about TensorFlow placeholder in the video before the previous, I think. It's in video 11 or 12, maybe, I don't know, actually I don't remember. It's but we talked about placeholder in one of those previous videos. So this is video 14, so it's supposed to be video 12. So in video 12 we talked about placeholders, I think. If it's not 12, then it's 11, I think. So for the placeholder, the first input is the data type, right? So we're gonna just use a float32. And then the shape. Of course, the shape is optional, but nevertheless, let's give it a shape so that our code is more explicit. The shape, so capital X is gonna be 2-dimensional, right? It's gonna be 2-dimensional. It's a matrix. the number of rows, we don't really know what's going to be the number of rows yet, because we haven't actually decided how many batches we want to divide the 10,000 rows into, right? So the number of rows can be any. So let's give it none. And then the number of columns, right? So X is going to come from the input data with bias, right? All the values, all the elements inside of the X is going to come from this particular matrix. How many columns do we have for this particular matrix, right? So input data has n these many columns. That's 2, right? And then input data with bias is the input data concatenated with 1 column in front of it. So input data with bias actually has 3 columns. So X is going to come from, all the values inside of X is going to come from input data with bias. So X must have 3 columns, right? But instead of using 3, let's use n plus 1 as the column number. And again, let's provide a name, right? And then y equals to, it must also be a placeholder. Let's also give a float 32. And then the shape, again, the number of rows is any. And then it must be 1 column. It's a ground truth vector. It's just a one-dimensional thing. And then the name equals to y. So the number of columns are fixed for both x and y, right? But the number of rows is can be anything, can be any number, because there can be any row number depending upon the number of training examples in each mini batch, basically. And we also need a TensorFlow variable to store the weights w. So w, this part is the same as in the previous video. But instead of using the variable constructor, this time I'm going to use the, in the previous video I was using the variable constructor, but this time I'm going to use the get variable function. I'm going to use the get variable function and I'll give it a name, and then initializer. The initializer, we're going to use a random number generator, tf.random uniform, and then the dimension is going to be n plus 1, no 1, right? How many weights? It's 3 weights. N is 2. 2 plus 1 is 3, right? And then the range of the random values goes from like a minus 1.0 to 1.0, right? And then maybe let's give it a seed, 42. Random number seed. And that's going to be our W. So slightly different from last time, but in principle they are actually identical. Just to make this thing longer, maybe it's not possible. And now we can create the predicted output, y pred, by doing a matrix multiplication between x and w. So y pred is going to equal to tf dot matmao x and w, and let's give it also a name. Let's call it prediction. And this line of the code is identical to the last time. And then we have the error vector, or error tensor. Error is going to equal to y underscore pred subtract y. And again, this line is identical to the last time, to the code in the last video. And now we can create the mean squared error MSE from the error tensor. MSE is going to equal to tf dot reduce underscore mean, and then tf dot square, right? Error, and let's give a name MSE. So these 3 lines of code are identical to the last time, to the code in the last time, right? And this time we will use the TensorFlow out-of-the-box gradient descent optimizer. So we will not actually compute the gradients explicitly. So the optimizer will do that for us. And we're going to set the learning rate to 0.01. So learning rate, that's one of the hyperparameters. And it's also a required input for the optimizer. So optimizer equals to tf dot train dot gradient descent optimizer learning rate equals to learning rate. And then we can get the training operation from this optimizer. So here we are gonna get a TensorFlow operation, training op from the optimizer. MSC. And that's gonna be our training operation. And now we have actually completed the graph construction phase. But this time we will try to create the log files that can show us the progress of the training process in TensorBoard. So how do we actually create log files, right? We talked about how to create simple log files that involve just the log of the default graph, basically, right? But we didn't actually use the log file or the log event files to actually record the progress of the training process. The progress of the training process is actually given by the MSC, basically. So MSC should keep reducing, right, throughout the training process, with some fluctuations, maybe, right? But in the previous examples, we didn't actually do that kind of thing. So this time, let's try to do that. So in order to create log files, we need timestamps. So from datetime import datetime. So we're going to import the datetime module, and now we can create the timestamp and then combine it with the root of the log directory to create the complete log directory path name. So we're going to do that. So first, let's get the timestamp. UTC now. Let's just use UTC now. And then strf time percentage y, percentage n, percentage d, percentage capital H, percentage capital N, and percentage capital S. If you don't exactly remember the meanings of those strings, you can just Google. It's not really worthwhile to actually memorize all those the meaning of all those characters. So root log dir is going to be tf_logs. So that's just going to be a subdirectory in our current or working directory. It's going to be just a, and then the complete log dir is going to equal to, so we're going to use some placeholders. No, these are string placeholders, not TensorFlow placeholders. And then the format. Root log dir, and then now, right? So this way we can create the complete log path name, right? And in the past, we only used the log event file to actually display the computational graph constructed by TensorFlow. And this time we will add the MSC value to the log event file and monitor how MSC value actually changes through the training process. And in order to do that, we need to create a, in fact, a scalar tensor or a rank 0 tensor containing just a string. And this string will store a summary about the tensor that we are monitoring. So how do we actually create this this rank 0 tensor containing a string, right? Let's call it MSC summary. That's going to be That's going to be our rank 0 tensors with just one string in it. And then we're going to call the tf.summary.scalar. This scalar is going to take two inputs. MSE, that's a string that's we're going to use for displaying the MSE in the TensorBoard graphs. And then the second input is actually the tensor that we want to log. That's this tensor. This tensor is the stuff that we want to log. And that goes into the second input. And yeah, I think that's the only scalar that we want to log. And now we can create the file writer object. And this part is sort of similar to our previous videos that demonstrates TensorBoard, tf.summary.file writer, right? And then log dir, that's the path name, right? And then the graph that I want to log, tf. That's a default graph, right? It's a get default graph. And now we have actually completed the graph construction phase. We'll leave the graph execution code for the next video because the execution code is still quite long and involves defining another independent function. But let's just make sure that we didn't actually make any mistakes by running it. It looks like we actually made some mistakes here. It has no attribute gradient descent optimizer. Descent optimizer. What exactly did I do? Oh, typos, I guess. Oh, the spider has the autocomplete, I guess. I was using the autocomplete and okay, so now it looks like it's giving me a pass. So let me run it again. Okay, so it looks like it's corrected this time. So in the next video, we're gonna keep working on this code and finish writing the graph execution code, and also give it a test run or a few test runs and watch the output from the TensorBoard and see how the training process progresses.